In today's video, we're going to be looking at some demonstrations that relate to circular motion, things just moving in circles. For this first one, I have a tennis ball here, and I've poked a hole through it and then threaded a string and tied the string on. And so all I'm going to do is spin this tennis ball in a circle, but I want you to know what happens when I release it at the very top of the circle. So it'll be going in this circle like this. And my question really is, if I let go the moment the tennis ball is at the apex of the circle, right here at the top, what direction is it going to go in, and why is it going to go in that direction? Okay, let's look again. What if I release the tennis ball when it's here at the far right end of it? Well, if we're thinking about the velocity and what's happening, if I let go and it's right here, it should go pretty much straight up. Because at this point, even though it's moving along this arc, it's pointing in this direction. Well, why isn't it always just going up forever or to the right forever, depending on where it is? Well, it's because of this string that's attached to it. This string is actually applying a force. And so if we think about it when it's at the top here, sure, if I'm spinning it in this direction, at the top it's pointing to the left. But this string is pulling down on it, so the velocity is to the left, and the force is towards the center of the circle. In this case, it's down. That's going to actually change the direction of the velocity. It's going to change it from pointing this way to pointing over here, and then pointing over here. And as it traces through the full circle, well, the tension is always changing the direction of it. But unless I start pulling really fast, it's actually going to stay at the same speed. So the meters per second it's going is fairly constant here. Sure, maybe it's a little faster at the bottom because gravity's pulling down, a little slower at the top because gravity's still pulling down, but it's close to the same speed. Now, for our second demo, I have this bucket. And in the bucket, I've filled about 2 inches of water. Not a whole lot, but enough that I don't want it spilling on me today. And what I'm going to do is something you've maybe seen before, maybe haven't. And all I'm going to do is get a nice firm grip on the bucket so it doesn't slide. I don't want it smashing in the ground. And just gentle start. And there it is. Now, the crazy thing is that I can actually see the water in the top of the bucket, and it doesn't even look like it's moving. I don't even hear the water really. Now, if I start kind of getting a little violent with it, you can hear it sloshing now, sure. But the question really is, why is the water, when the bucket's at the top of its arc, not falling down? What is it that's keeping the water from falling? Because gravity's still present, right? So why is it that that's the case? And the even wilder one, maybe this is a bad idea, that I can do is if I started swinging it this way, but then start swinging it horizontally. And again, I can actually see the water in the bucket that's horizontal. The water should be falling out right now, but it doesn't. So why is that? For our third demo, we have this broom and this bowling ball, and the goal, and normally we have people compete with this because I have a few bowling balls, is we want to make it go in a circle. So let's just try a couple ways, and you'll see what is the easiest, best way to do it, and hopefully piece together why that in fact is the case. So we want it to go in a circle. Oh, okay, lost it. This is a pretty lame circle. Okay. Or
notice where the broom is facing. It's actually on the outside of the circle that the bowling ball is having to go in. And so it's actually just pushing towards the center. It's actually pushing towards my feet, in fact. And so in the case of this third method, this broom is applying what's called a centripetal force, which is a center-seeking force on the bowling ball. Now, for our fourth demo, our final demo here, it's going to use this lab apparatus we made last time. So we need to find the mass that is going to be used. And I can see here we're at 128.13. We could divide that by 5 and find out kind of the approximate mass for one of these. But really, I just want to show the idea here. And what I can do is just thread my paper clip through, kind of wrap it up here so it's nice and snug. Now, what we'll do is we'll grip it here, kind of on our glass tube. This will start hanging. We'll kind of hold it until the rubber stopper is spinning, and we'll start spinning it until we feel tension pulling up on the string here. We'll just start swinging kind of gently, and we can see that my arm's in the same place. If the masses are here, they're actually falling, and my stopper is going faster and faster. I'm not even moving my arm. So I wasn't spinning fast enough. Gravity pulling down was stronger than tension pulling up here on it. And so I can start spinning a little faster. And if I spin too fast, well, now we can see that the masses have actually kind of gone all the way up towards the top. And now we're getting kind of this funny swing going on. So you want to find kind of a nice intermediate. Once we do the lab, we'll actually put a piece of tape on the string here so that we'll keep the radius of the circle of the stopper the same. But this is the whole idea here, that if I swing too fast, the mass goes up. If I swing too slow, the mass sinks down. And if I swing kind of just right for any given radius of arc for my rubber stopper, we get it so that our masses just kind of float here in space.